Project is Battery Analytics System. This is the problem statement: to develop a system that is effective at obtaining real-time battery data, estimating battery life, charging and discharging times using machine learning, IoT devices, and applications for collectively displaying all the assets. Here are a few of our competitions: OptiWatt, EV Notify, among others. This is the data flow diagram of the user when he uses the application, the DFT diagram of our IoT device. Now coming to the human-computer interaction component, the pie chart shows the key usability issues faced by our users. The bar graph shows the survey result that we got from our questions. Here is the heat map of our users while using the application. And here are the design principles that we use to create our features. This is the MAD part, where this is the overview of a Flutter application. This is the authorization page, the home screen, settings and stat page, battery info page, where machine learning comes into play. Once you have updated the battery capacity, you can get a cycle number, the remaining useful life, and state of health percentage. Here is the context diagram where once the user enters his battery capacity, the input goes to the server. From there, it goes to a machine learning model via Flask API, through which it goes to our Flutter application, and the results are shown to our user.
So talking about the business understanding, that is a part of this PPA. There's a two areas: one for user, as a user, one for as an industry. For users, users can see their battery stats in real time, the remaining useful life, the battery current life, the capacity remaining, and other things like temperature. And all. On the same app, for industries, this can be useful for taking out the inputs and predicted while what things, what factors, what batteries assets are affecting the battery life and everything. So they get a real time data. So this can be the advancement and modification in their battery. So this is data understanding. This is the data we have taken from the NASA, and according to that, we have tried to create a prototype also. Description about it contains columns like data, temperature, voltage meters, voltage load, current load, volt, etc. We have done the pre-processing modeling. This is the one of the main part. Modeling, we have tried different model algorithms to implement, like linear regression, support vector machine, random forest, decision forest, lasso, and all. And to evaluate that which one is best for us, we have tried R square, root mean square method, MEP. So on the basis of this evolution, we have concluded two models for our prototype, that is SVM4 SOH, that stands for support vector machine. And as you can see here, this graph shows the variations in the prediction, that is colorful lines with the percentage of train data given. Like in for 40-60%, we can see here red line is the prediction, and like this we have shown with a different type of parameter. So hyper tuning is one of the part we have worked on SVM with the training data, number of iteration, number of is on gamma and all. So this is what we have worked in the SVM part to predict the SOH. And second is lasso regression, that is for RUL. Same thing as we have done in SBM, we have also implemented the same concept here. And as you can see in the graph, it's also showing the same thing, the different prediction of the model with a different number of different percentages of data, as red represent the 60% of trained data. And now talking about the evolution time, as we have already talked about, we have used different evolution metrics to compare our model. So one of the metrics we have shown here is MEP. So as we know, for the MEP, the value should be considered as less than 5, that will be considered as good. So as here is the output. And as we know, MEP stands for mean absolute percentage error. But as you can see, linear regression has a minor rate, 0.000 something. But as we go towards train and test accuracy, it was overfitted towards training data. That's why we need to drop linear regression. And from the remainders, we can see that last and support vectors are the one who is having the less than 5 MEP. So this was regarding the ML. And talking about model deployment, we have converted our model into a PK file and hosted on a local server using Flask API. And this is the on your left hand, this is the code that shows that the one of the function of the code of the Flask API, how our model is implemented on the local host. And on the right side, this is a part of function that is used in a Flutter to connect that local host API model to the to the app to get the outputs. As we can see here, we will run our Flask in local output that is given here with the IP address here, and we will call this function here. And if I run this, our API is running on this IP address, which is located on local server on the machine only. So we will call this API in our application, Flutter application, as we have passed this, it is here. And now if I try to predict the values, let's change this to 1.4. And as you can see, the value changes here, and it is the prediction of what exactly we want. And also we will get the values in the console also. So this is how we are connecting our model to the Flutter app. This is our prototype for testing the real-time capacity of the battery. So for the prototype, we have taken compared with the data and the prototype of the NASA. So we have tried to configure with that prototype and data. So we have used 2000 mAh battery and provide a constant load of two resistor. One is 2 ohm and another is 4 ohm. So this is a MOSFET which will maintain the flow of current between the source and the destination. This 16:2 LCD. This is potentiometer that will control the brightening and the intensity of the LCD. Then this we are having the Arduino where all our codes and the connection has been done. It is the source of the root and the code for the whole uh, prototype. So through this we are going to capture the real-time capacity of the lipo battery at terminal voltage of 2.7 with a constant load and environmental factors. This is working of our prototype. As we can see here, we are able to see some few parameters that are real-time voltage as a 3.64 15 milliampere. That is the capacity drain from the battery. This is the current provided to the battery, and this is the time it has been run for. So as we run more and more, we will get the more data, more accuracy will be provided, and the indication of LED here will tell this the process is currently going on. The battery is going to degrade. Once it stops, that means the battery has reached the level of its depletion. It will not degrade furthermore because it is a threshold value we have set it.